Okay, anything else? Okay, then it's time for our speaker of the evening. Our speaker tonight is Dr. Ralph Milliken. He's a professor in the Department of Earth, Environmental, and Planetary Sciences at Brown University. His research interests include understanding the origin and role of water in the formation and evolution of the solar system, and the use of remote sensing techniques to determine the composition and geologic history of the planetary bodies. Please help me welcome Dr. Milliken. His talk tonight is Red Light, Blue Light, Return Samples from Near-Earth Asteroids and Implications in the Search for Key Ingredients for Life. Welcome.
All right, so thank you so much, everybody, for inviting me to come speak this evening. I was trying to remember, it's been quite a while since I've been able to come out and join the group and talk, and I can't remember what the topic was last time. It was either the Curiosity rover, my work on that, or it might have been the Hayabusa 2 mission that the Japanese Space Agency JAXA had. I think it might have been Hayabusa 2. And if so, then we'll have a little bit of update about that tonight. But what I'm really going to focus on the kind of back half of this story that I'd like to tell you, has to do with NASA's OSIRIS-REx mission. So I'm just out of curiosity, how many of you have heard of the NASA OSIRIS-REx mission or things? Okay, great. So we've got some hands there. So, well, you'll certainly hear more about it tonight. Basically, these two missions that I'm going to talk about, they went to near-Earth asteroids, and I'll tell you the type of asteroid that they went to. And although they did a lot of amazing observations up close at the asteroids to study them, the fundamental goals of both of these missions was to grab material from those asteroids, return that material to Earth so that we could study it back here on the ground in great detail. And we'll talk a lot about that tonight. And it's all kind of going to wrap around this idea of like, well, why do we do this? First of all, why do we spend the money to go grab pieces of asteroids? And what do we learn from them? And what does this have to do with our understanding of the kind of origin of life and ingredients that one needs for them? So, you know, I like to start this off. I know people in the audience might have very different backgrounds and kind of knowledge. So we'll start off relatively straightforward. Might be a review for some of you, but that's okay. So first of all, why meteorites? Why do we even study meteorites at all? I'll probably maybe preach to the choir here because we're all kind of interested in space, right? I know I like rocks as a geologist. I'm trained as a geologist and now a planetary scientist and geologist. So meteorites are like doubly great for me. They're rocks and they're from space. Well, a fundamental aspect about meteorites is they record the very earliest processes in our solar system. They provide an understanding of how our solar system and everything in it came to be, how planets in general form and evolve. And if we can understand that for our own system, the solar system, this might, of course, have information about other planetary systems, exoplanets. Now, there's a subgroup of meteorites that'll be the focus of our discussion tonight called carbonaceous chondrites, named such because they have carbon in them. They're known to have organic compounds, other kind of very interesting components. These, out of all the meteorites, truly are some of the most primitive things we have, and they actually hold the components that we use to get the age of our solar system. So these are meteorites that are older than the planets. They represent some of the earliest building blocks we have, and along with comets, are the primary source of water and organic compounds that would have been delivered to the inner solar system that we know we need to kind of get life going, right? So these types of meteorites, or I should say, the asteroids from which these types are derived, those in comets are what we call volatile rich. They have lots of water, organic compounds, and we're very interested in understanding where these objects are, how they formed, how they evolved, how they're different as you go from close to home here at Earth and deeper out into the solar system, and how they've changed over time. Now, the kind of one of the main tools that I use, and in general we use to kind of understand these meteorites and asteroids, would be reflectance spectroscopy. So any of you look with a telescope, you're looking at reflected sunlight primarily off of objects, or emitted energy if you're looking at the longer wavelengths. Well, we do this in the laboratory as well to compare to spacecraft data or to telescopic observations. And we like to use reflectance spectroscopy because, one, it's just relatively simple to use. Certainly at the visible wavelengths, it's quite easy. Nowadays, we have an also pretty, I should say cheap, a lot cheaper than they used to be, detectors in the near infrared and longer wavelength regions. So it's something that's very accessible to us. There's a long tradition of just huge data sources to go back and look at this. And it's one of the primary ways that we can do measurements of this in a laboratory of meteorites, measure how they reflect sunlight or light in a lab, and compare that to telescope observations or spacecraft observations of all the asteroids out there, and looking at how they're reflecting sunlight and see how they compare and how they match. And so it's a way by which we try to link the meteorites to possible parent asteroids and understand what types of materials are out there and where. And that's basically the question of, well, which meteorites come from which asteroids? That's actually exceptionally difficult to answer. There are a couple groups of meteorites we can hold and point to that we have a pretty good understanding of. They came from this asteroid or that, but usually extremely rare. For any given meteorite, we do not know which asteroid it came from. All right, and most carbonaceous chondrite meteorites, the ones with all these volatiles and water organics, we don't know which specific asteroid they came from. We only know them as categories. So that's a tricky one to address, but it's something that we can try to get a little bit more traction on, we hope, by getting these return samples from asteroids. So, of course, then you might ask, well, hey, if we have all these meteorites and we can do all this work with them and pick them up and study them, then why spend so much money to go and grab something from a piece of an asteroid? Well, for these specific, or another way to think of that, to frame that question is, what are we getting from this sample? And this is the sample capsule opened up here in the Clean Lab at JSC from the OSIRIS-REx mission. What do we get from this sample that we can't get just from meteorites that we pick up off the ground? And so there's a lot of material in here, all this dark material. That is material grabbed from the asteroid Bennu by the NASA OSIRIS-REx mission. And here's just a close-up of one of these little fragments, kind of show you what it looks like. And that's something we are still analyzing. Well, the reason is, these things, these carbonaceous rich materials and volatile rich materials, they are extremely sensitive to our conditions here at Earth. The atmosphere, so things oxidize rapidly. They don't worry about that out in the cold vacuum of space. It's a lot warmer here. There's a lot more water here, water vapor. So there are very sensitive materials in these that degrade very rapidly. And so you can take a pristine object like this, and it can just turn fresh to rotten, as the article says here, just 50,000 years. Some components we know leave almost instantaneous. The second it lands on Earth and is exposed to our atmosphere, you've already lost important compounds on there. They're really volatile. So what we want to do is grab it in its most pristine state from the asteroid itself, return it in controlled conditions, keep it under kind of vacuum or nitrogen conditions, so we can really understand what is the inventory of stuff out there, the kind of the building blocks that we think about for life, what actually exists out there on these asteroids. All right, so this is why we're interested in these sorts of things. And we have two missions that we'll focus on. Again, the Hayabusa 2 mission that the Japanese Space Agency, JAXA, had at the carbonaceous asteroid Ryugu, and then NASA's OSIRIS-REx mission at asteroid Bennu. And again, both of these are near-Earth asteroids. The OSIRIS-REx target Bennu is also one that does have a non-zero probability of impacting the Earth, but not for a long, long time. It's like 180 years or something. Don't worry about it. And even then, it's a very, very low probability. But I'm not going to be here soon. 180 years out. So part of this mission is also trying to understand the near-Earth asteroid population in terms of security for Earth, in the realm of what we often refer to as planetary defense. Understanding the properties of these asteroids and their composition, their physical state, so that we can get a better handle on, if we need to deflect one, how would we go about doing that? What would be the best path? And I'm not going to talk about it tonight, but NASA had a whole separate mission called DART, the Double Asteroid Redirect Test, where they actually impacted a small component of a binary asteroid, and they did deflect it to kind of demonstrate that a kinetic impact event with enough warning time can deflect something, move it off of its path. So again, if we had enough time and warning that an object of this scale were to strike Earth on a path to do that, we at least now know that we might be able to move it out of the way through a kinetic impact. But that's a story for a different. All right. So just as a preview, so with these samples, again, one of the main tools I use in my toolbox And by me, I mean my graduate students and postdocs, because I wish I had time to get in my lab, boy, let me tell you. I feel like mostly just the financial manager a lot of times these days. But what we do is we work with a lot of materials, extraterrestrial materials or astro materials. So this would be Apollo samples, lunar meteorites, other meteorites, and now these kind of asteroid samples. We measure them with our spectrometers in the lab, primarily looking at reflected light. Sometimes we will look at thermal emission of objects as well, and we'll get squiggly lines and patterns that look like this. And so just as a note, so I'll show a bunch of plots like this, but on the x-axis, we're always going to have wavelength. So the shorter visible wavelengths will typically be off to the left, the longer wavelengths, lower energy near infrared range off to the right. And then the y-axis is simply reflected. So that's just the amount of light that it is reflecting. Of all the light that hits it, how much is it reflected? So this blue squiggly line here, this is an Apollo 17 rock from the moon, and it reflects on average from visible through near infrared about 15% of all the light that hits it. And this black line here is soil from the Apollo 17 set. And note, it looks extremely different. Presumably, this soil is derived from just the pulverization of this type of rock over geologic time, but it looks very different. What we'll note here is that, first of all, it doesn't have these strong dips and absorption features that be kind of smeared out and removed. And it also increases in reflectance. It gets brighter as you go to longer wavelengths. We often will refer to this as something that has a, quote, red slope, meaning that it is brighter at the red wavelengths out here relative to the blue wavelengths. If it were sloping the opposite way, we would say it was spectrally blue, right? So this difference here is due to the role of what we call space weathering. Even in the vacuum of space, you have processes, micrometeorite bombardment, irradiation by the solar wind that modifies the surface of these airless bodies over time. We know this very well for the moon and understand how it works. The same process must be occurring on all of these asteroids as well, because they don't have atmospheres on them. But we don't actually have a good understanding of the specific mechanisms and results of what happens on these types of asteroids, because they're made of different stuff than the moon. Right? But we'll come back to it. All right, so we do a lot of stuff in the lab. So back to actually asteroids and kind of thinking about ground-based observations. So there's been a number of kind of classic classification schemes for classifying all the asteroids out there based on their reflectance properties and telescope data. I like to show this chart because it shows you how things have evolved over time. So one of the most famous ones would be the Tholen classification scheme from the 80s, based on a handful of different wavelengths. A lot of times telescopes, camera systems might just have a few different filters at which they're getting that light from to see it. And that would be represented by these orange kind of squares here for these different asteroids, say like the asteroid 4 Vesta, one of the largest objects in the main belt. Ceres is that, well, dwarf planet Ceres, the most massive object in the main belt. And so we have those orange squares, but over time with improvements in instrumentation, detectors, technology, we can get many, many more wavelengths, and that's shown in the black lines behind it. Again, observations of those same targets, just showing you how much more complex the reflectance patterns are for these objects when you have access to that data. And by doing that, you can actually get much finer classification schemes. One of the ones that a lot of folks rely on now was kind of conceived of by Bus and Rick Benzel out of MIT in the early 2000s, then really enhanced by Francesca Di Meo after that. And the difference here is using much longer wavelengths, particularly out to the near infrared region, you have way more information to be able to discriminate between these objects and link it to possible types of meteorites that we have. Now, all of these schemes, though, they're what's fundamentally differentiating the kind of alphabet soup and taxonomy of asteroids has to do with the curvature that you see of different asteroids, their slopes, their curvature, and general shapes. So don't worry too much about the details. You know, this is what I say would be the alphabet soup of classification schemes for asteroids. It used to be that there were just S-type asteroids, and now we recognize that these S-types are actually, there's subdivisions, so it's called an S-complex. But the ones we're going to focus on today are this group of asteroids that we think are linked to these carbonaceous chondrite meteorites. These are the asteroids that are really dark. We think that they are enriched in volatile compounds, water-rich minerals, potentially ices in some cases still, and organic compounds. Again, the raw ingredients that we need for life as we know it. That's the C complex. And you'll note here that most of these have this quote red slope. They get brighter as you go from left to right, from shorter to longer wavelengths. But there's an outlier, and that's this guy here. These are the B-type asteroids. They're not that common, but they're there, and they do stand out in this taxonomic scheme. They don't really fit with any of the other groups, so they do fit mostly in the C complex. They're very dark. They have other kind of properties like the C-types, but they're blue. So it's very different and distinct. And the reason I'm telling you the story is because, as we'll see, these two asteroids that we went to, the Japanese mission went to a classic C-type with a red slope, but the NASA mission, OSIRIS-REx, wasn't able to go to one of those. The one that they were able to target and go to on the timeline turned out it was a B-type asteroid. So they're just fundamentally different, which is great. We can actually try to understand, well, why are these things blue sloped? It's kind of weird. We don't really see that in any meteorites when we measure them. We don't have an analog for that meteorite collection. It's very odd. So we hope to use this information to understand what this all means. Now, a word of caution here, that when people talk about things being red or blue or it's C-type or B-type, you really have to be careful, it turns out, as to what wavelength region are you talking about. Historically, a lot of these initial schemes of classifying were based purely on visible wavelengths. And as you can see, asteroid Themis, it is blue in the visible range. But when you get the near infrared data, it turns up and it becomes red. So this is a classic example of an asteroid that would be a B-type in the kind of typical scheme, but it's much more complicated than that. That actually it shows there's something different happening at the longer wavelengths. And we compare that with a different asteroid, 2 Pallas in the main belt, which, although it has a lot of structure in here, it is generally negative or blue slope throughout, for both the visible and the near infrared. So there's a lot of differences. So we have to be careful what we're thinking about. The asteroid Bennu would be more like Pallas here in that it is blue slope throughout its visible and near infrared. Very distinctive characteristic. All right. So one of the fundamental questions we have then is, what is driving this difference? Why are some of these carbonaceous asteroids red sloped? Why are some of them blue sloped? Can we understand what's driving that? Is it important? What does it mean? Is it because of spin weathering? Is it because of the composition of these bodies? What's driving this? And just to show you some of these carbonaceous meteorites, C-chondrite meteorites, this is just kind of a bit of a rogues gallery of what some of these look like. They're generally very dark. They have bright materials that can be kind of, peppered throughout them. And again, they'll have inclusions and things in here that are various ages. But these are effectively, they are sedimentary rocks, is how we might classify them. Most importantly, though, a lot of these show evidence of alteration by liquid water. So these are interpreted that they originally formed on planetesimals that were probably 1 to 200 kilometers in size, forming beyond the current main belt, beyond the snow line, where we're condensing ices out and rocky stuff out. We have short-lived radioisotopes on here that are producing heat on short timescales. That heat early on, within just a few million years, melts that ice. So the ice becomes liquid water. The liquid water then is altering the original rock to kind of make a muddy soup-like material almost, and forming new minerals. So this is what's happening on these objects just in the first couple million years of the start of our solar system. And it's giving rise to complex organic compounds as well. So keep this in mind. And so it gets complicated. These are some data from our lab by one of my recent graduate students, Cody Schultz, who's now down at University of Central Florida. These are elemental maps of meteorites, carbonaceous chondrites, and they're not homogeneous. It turns out these are extremely heterogeneous, and in fact, a lot of these turned out to be breccias. They're fragments of rocks that were broken apart and then welded back together on these parent asteroids that they come from. So they're extremely complex rocks with very complex histories. And we're trying to decipher what that means. And in some cases, there's evidence for multiple periods of interaction with water. Sometimes that water is salty, sometimes it's a little less so, might be different pH levels, this sort of thing. So very complex histories. Now, this gives us some challenges because when we we try to categorize the meteorites, we generally historically have categorized them by, well, how altered are they by water, more or less, so forth. And people will give them a number category, say type 2. And a type 2 would mean it has a lot of evidence of water rock alteration interaction. That's great. So my colleague, Dr. Takahiro Hiroi in our lab, kind of was doing a survey a lot of these meteorites that were all classified as a similar type of meteorite. And this is what we see in the lab. Each red line here represents a different meteorite. And all I want to draw your attention to is that they're not exactly the same. There's actually quite a bit of difference and variation within here. And so that already is telling us there's a lot of variation within these meteorites that we're currently classifying as roughly similar. So what's driving that? And the feature I'm focusing on mostly here is at a wavelength of 3 microns, or 3 micrometers. This is often what's called the kind of water or hydration band. This is an absorption, so it's reflecting less light, it's absorbing light here, and it's due to H2O, molecular H2O. We also, when we say hydration, we will also mean OH, hydroxyl. So we can have OH plus or minus H2O, and this is in minerals that are in these materials. So again, evidence of liquid water interacting with the original material. And we do see evidence of this on some asteroids. The trick is, some of the most important information is right around here at this wavelength. And that's tricky because that is blocked by Earth's atmosphere, the ground. And so that is something we cannot see through. So here are telescopic data of some of the larger objects out there in the main belt. My colleague Andy Rifkin, the Applied Physics Lab. And we just do not have information here that is not accessible from the ground on Earth. We can only access data in that region by getting outside of our atmosphere. Yet that is a critical region for us determining, is something dominated by OH, H2O, what's the relationship here? And so this is something that right now, for most asteroids, we just don't know what they look like. Okay. But we know that there's a lot of variation. So just like the meteorites, we see within the carbonaceous asteroids, even in the largest ones, there's some weird wiggles and absorptions in here, and there's variability. But what's driving that? These variations in the hydration region, what is the fundamental cause? So that brings us to the prime story then with that backdrop. We have these 2 asteroids, near-Earth asteroids, the B-type Bennu, observed by OSIRIS-REx, and the more classic C-type Ryugu, observed by the Japanese Hayabusa 2 mission. And again, Bennu is blue-sloped, Ryugu is red-sloped. These are not to scale. Both are less than a kilometer, but Bennu is about roughly half the size or so of Ryugu. Either one, if it were to impact the Earth, would be kind of a regional scale devastation event. These are, it would be a significant amount of energy and would not be great. Let's leave it at that. On the B type, what's interesting is that looking at its kind of reflectance data, we'll see that there's evidence for OH and H2O on Bennu, whereas on Ryugu, there's really only evidence for OH. That's a bit disappointing. We were hoping it would be more water-rich. And as I'll show you, when we got there, we just didn't see that, which was a bit of a downer, at least initially, we thought. But these asteroids, I will say also dynamically in terms of their orbits and how they're orbiting the sun, it is permissible that they actually came from the same original parent body. And what both of these asteroids are what we call rubble piles. Just looking at them, you can see they look very kind of knobby and blocky. And that's because these are not solid objects. They are extremely porous objects. What they represent is an original planetesimal that was roughly 100 to 200 kilometers that was catastrophically shattered. Pieces then reaccreted and reformed under gravity, and they're simply held together now as loose piles of rubble by gravitational and frictional forces. So their overall bulk density is quite low. They're highly porous. And basically, like when the OSIRIS spacecraft went to touchdown and grabbed a sample, they related to, it was kind of like jumping in like a ball pit at Chuck E. Cheese or something. It was sinking down that much. They actually almost lost the spacecraft, and it was backed off after it hit a trigger point at the last moment. Yeah.
Yeah, I have a question. So you must be taking a whole bunch of these pieces in order to find the average solidity of them, because obviously, if they're scattered and they've been put together, taken apart all together, there must be a lot of variation among the samples.
Okay. So the comment is like, sampling these asteroids and the variability. So it's an interesting question because before getting to these objects, some of the carbonaceous kind of meteorites we have are actually quite homogeneous, and people had proposed these objects might be extremely homogeneous. Maybe it doesn't matter so much. We now know that's not true for these, that there's actually much more complexity happening in the original asteroid, and that is carried through to these rubble piles. And it's something we observed with both spacecraft, but it wasn't necessarily, not everyone would have predicted that that is what we would have seen before we got there, actually, because of the meteorites and I think some biases in that. But it does turn out they are quite diverse in that regard. We do not have a lot of sample. As I'll note, we only have 5 grams returned from Ryugu, so that's not a lot of material. We have like 120 or so from Bennu, so more, and it has greater diversity in there because we have more material. But the question still remains: the material that we actually returned and analyzed, how representative is that of the object as a whole? For Ryugu, we think it's pretty representative, and I'll show you why. Because for Bennu, there's still some questions about that, and that'll be part of the interesting story. Okay. And I'll say both of those objects show evidence for space weather. Again, they've been exposed to the vacuum of space and micrometeorite bombardment and solar wind implantation for millions of years. Okay, so here's kind of a stretched out map of what these objects look like. Bennu and Ryugu, they both have actual like kind of diamond top-like shapes with these equatorial ridges, which is intriguing. That tells us something about the dynamics and how they've changed over time. Both have variety of boulders, as we just mentioned, so a good segue there. And you can see some of them even have kind of a salt pepper type, coloration to them. Now, in some of these images, I'll note things will look relatively bright and other things relatively dark. I assure you, it is all exceptionally dark, right? These asteroids, and especially Ryugu, which is a little bit darker than Bennu, they are darker than anything you could look at in this room that's black, or even the night sky. The Ryugu is only reflecting about 2% of all the light that hits it, right? It's exceptionally dark. These images and the cameras are designed to pick up subtle differences, and they're highly stretched contrasted. But things that look bright on these, that's the difference between reflecting, say, 2% of light versus 2.5%. It's all really, really dark. And when you look at it, and if you're ever on campus, you can come, we can show you, it just looks like charcoal, but even darker. It is exceptionally dark. All right, so 120 grams from here, 5.4 from here. And let's talk about what we see. So again, being someone interested in the reflectance properties, and spectroscopy is a primary tool by which we're trying to understand the composition of these, this is what we saw when we got to Ryugu. Again, 3 microns out here. We're hoping to see this big absorption due to water, and it's just not there. All we see is this tiny little dip here, and we spent a lot of time calibrating. It is real, and it's kind of zoomed in here. It is this feature here. It is a real feature. It is exceptionally weak, and that is just due to OH, hydroxide. We see this in a lot of carbonaceous conduit meteorites, but it was a bit disappointing at first because there's just not a lot of evidence for a lot of water. So one thought is maybe it did have that water, but it was orbiting closer to the sun at one point. It got dehydrated, kind of baked out, and it lost that water at its uppermost surface over geologic time. That could happen. That was a theory. But it just doesn't seem like it has a lot of water on it. Might not be quite as volatile rich as we had hoped, but a little late now. So you're going to grab the sample and do the job anyway, because that's what the commission is focused on. But what's also interesting is that the object as a whole, Ryugu, it's extremely homogeneous. Basically, all of the spectra look like this. This is the average over, but when we look at individual spots, they all look basically the same. And you also note it has this gentle red slope to it. Well, so that was predictions. Of course, you can start to get a little bit nervous maybe if you were a person like me, colleagues who wrote those papers and predictions, and then they actually return the sample, and you can measure it in the lab, and you're like, I hope it kind of looks like what we said it was. So here's one of my favorite images from the mission. This is after the touchdown event, grabbing the sample. This is the shadow of the spacecraft as it's lifted off. And what you can see, then these blobs here are from material that's just flown up around it. And it actually got darker after we did the touchdown event. right? So it's only reflecting 2% of light to begin with, and then it got even darker afterwards.
Just out of curiosity, how big is the space?
Ooh, the spacecraft, that's a great question. I have no idea. It's,
Just a good.
I mean, it's not like this big. It's a pretty good size. Is it as wide as this room with the solar panels on it? Might be, I think. But, yeah. Yeah, that's a good question. I don't know the full diameter of it.
Is there a professional courtesy amongst all the nations who are capable of bringing back samples who have gone to the moon, of sharing some of their material, like you have some of it at Brown?
Yes.
How does that work? I mean,
Yeah, great question. International collaboration and partnerships are absolutely crucial to any of these endeavors, I think. And even though, NASA, the kind of largest and best funded space agency, could do this on their own, they often don't. I think, it's the right scientifically, it's much better to partner with people and all of their expertise. I'd say it's been very fun to be part of these two missions because they're both strong connections between JAXA and NASA, and they had formal agreements to exchange sample between the two nations. So some of the Japanese sample, NASA has, and people here in the US have access to study, and likewise, there's a percentage, a fraction of the NASA sample was exchanged and sent to Japan for them to study as part of their collection. So there was a long kind of standing formal agreements during the development of these missions to kind of really strengthen those partnerships. And the Japanese mission itself was also a partnership with the European Space Agency, ESA. And so there's all of these have a strong international collaborations to allow that exchange of sample and get the most and best information we can. Likewise, the Apollo samples are a little bit trickier for the lunar exploration. That said, actually at Brown here, we were one of the few groups back in the day to actually measure, it wasn't me, but colleagues measured the samples from the Luna samples from the Soviet missions that returned samples from the moon back then. But we don't have more, they percent, but we try to do work like that.
when you talk about the meteorites and the spectral analysis of the meteorites, and then talk about the sampling, is there any enormous database of all the meteorites that we have in collections that
Yes.
have the spectral analysis done?
I'd say two answers there. One is there is absolutely a whole catalog and well done by the Meteoritical Society. There are bulletins they put out of all of the meteorites collected through the National Science Foundation NASA-funded program that collects meteorites down in Antarctica. And people can request those, analyze those, and they have all sorts of information about those. How many of those actually have spectral data? Our lab, the one that we run at Brown, the NASA-funded lab, is the one that's measured more than anybody, and we've measured hundreds of them, but that's not even close to like the total thousands that are out there in the actual collection.
Does that go into universal database?
And that
other
is an
people-
online database for the world to see, and I'm happy to send those links to you. Yeah, we put it on there and we've made it, it's made publicly available for everybody to see. And nowadays we do photos of the samples and everything like that as well. So you can see it. And a lot of people, actually, more people use our database for their work and research than actually send us samples nowadays. But it's job security of some form. Yeah, but that's all out there. Everything we do publicly. Great questions. All right, and then the sample analysis plan didn't go quite as smoothly as we had hoped because of the timing of things. The original plan was we were going to fly out to Japan and get the samples there and hand carry them back to the US, and all safe and sound. Instead, we just FedExed it all because of COVID. Yeah, that's right. FedEx is good. It worked. A little nervous, but it worked out just fine. Yeah, I always like the part they're like, oh, does the item inside have any kind of value? And I'm like, I don't know what to tell you, like $180 million. Can't insure it for that. So just say it's just a rock. Yes.
How do you maintain a cleanliness so that these things are not affected by the atmosphere of the earth?
So for some of these, we don't at some point, we break that chain of cleanliness and contamination. We know that they will be exposed to the kind of atmosphere. Otherwise, for other samples, they are kept under vacuum or colder conditions and under pure nitrogen. So it just depends who's doing what kind of analysis and whether they've gotten the green light. Like, yes, we understand this sample will be exposed to the air and it's marked and noted, and people just know, it has been compromised for other types of things.
But when you talk about the comparison of these samples to meteorites that have been on the earth for who knows how long,
Yes.
you have to do some interpolation.
Yeah, and we do know from other analyses, we've done a lot of meteorites, that most of the water-rich things we see in there, they're all horribly contaminated. It's all Earth. It's all. So what we see, what we have now recognized is some of these hydration bands we see in the meteorite data, you probably can't trust any of them in being representative of what is actually out there on the asteroids. They're all just horribly contaminated. Which is why we're so excited about these, to actually see what does it really look like when you don't have that concern. All right. Here's just what some of the material looked like up close. Let's get that. And here's just some lab data from a different lab showing you what it's made of. The point is, it's a carbonaceous chondrite. What's fascinating though, there's even further subdivisions of carbonaceous chondrites, and there's the rarest type we have, where we call these CIs or type 1s. They're the most aqueously water altered ones of the bunch, but they are also the most isotopically and elementally pristine. They are the ones that actually, if you take all the elemental abundances of them, they match the solar photosphere. So we use these types of meteorites as our best estimate of the bulk composition of what our solar system started from. But they're very rare, those types of meteorites. There's only like 5 or 6 or 7 of them. This sample matches those. It is that type, which was not expected at all. But yet there it is. And we also know it's got lots of water-rich clay minerals in it, some salt phases. So these are the ones that are most altered by water, and they're rarest, but yet this is one of them. Water on the object, not from Earth, I should say. There's no evidence that this thing was heated up by any strong degree. And there's lots of amino acids and complex organic compounds. And in terms of what does it look like in the lab, well, it looks like this. So these are data from our lab. And effectively, it's actually a really good match to the spacecraft data. Now, this sample, going to the question we just had, this has been exposed to the terrestrial atmosphere. And so we actually have a bit of a bigger absorption feature here due to H2O from Earth. But it's this sharp, narrow feature that matches very well with the spacecraft data. If we compare it to other data that were acquired at the JAXA curation facility in glove boxes and nitrogen and so forth, this is our spacecraft data in the black lines. And here's the lab data measured under controlled conditions. So a beautiful map. So we got it right. At least, right, the spacecraft data were good. Interpret. It still raises the question of, okay, there's actually very little H2O on this at all. It's almost just OH. Okay, but it's extremely enriched in OH and water, OH-bearing minerals. All right, so Ryugu, we confirm like this object, it is a C-type asteroid. It's one of the rarest types that we have in our meteorite collection. Complex organics. It's clear evidence of water-rock interaction. It has a lot of hydration in it, but not H2O. So that's very different than what we had expected. But again, very consistent with the kind of pristine solar system materials. Now, what about the OSIRIS-REx mission? So first of all, I have to note, I love the artist's conception here of what everybody thought would happen before the landing. Note how it looks nice and smooth, and you got these, there's some rocky stuff there, and it's like, yeah, that is not what anybody saw. The same was true for Ryugu. I remember when we were out there, the first images come by, like on both missions, all the engineers are just like, oh, insert whatever word you will after that, because right, it's like some of those, as we'll show you, some of those boulders on Bennu, you can't tell because it's hard to get scale. They're the size of this room or a house, and you do not want to like just take your $2 billion spacecraft right down there and mess it up, right? So there was a lot of extra work that had to go into making sure they could find a spot on both of these objects to touch down safely without damaging the spacecraft, get the sample and return. And it worked great in both cases. So Bennu is just very different though than Ryugu. Again, it has this blue slope, the red data here, the red, that's from telescopic data, and the black one is from the spacecraft. So it has a sharp feature here due to OH, but it's also much broader, much deeper, much more in line with some of these meteorite data that we have measured in the lab. So unlike Ryugu, this is like, yeah, it kind of looks like carbonaceous material, big water bands, probably a lot of volatiles. That's fine. Okay, cool. We'll get it. And we'll see which of these it really matches, but it definitely looks very different from the Ryugu data. And again, this is kind of false color samples, just showing you the kind of slopes. Again, blue colors here means it is a blue sloped, red reddish tones mean it's maybe not technically positive red, more like less blue or flatter spectral slope, but the object is fairly homogeneous in terms of its spectral slope. It is blue, very different than review. After sampling, this was the kind of crater that was sampled. It actually became, that spot became a little bit redder, or I should say less blue, more flat, but still didn't really look anything like Ryugu. And here's a little animation of it. Again, it's a rubble pile asteroid, so it's a pretty energetic event collecting the sample. So a lot of materials flying up, and you can see that kind of bright and dark material. And so it's diverse there, and there's breccias and all sorts of complex rocks. And so one of the first questions is, well, what do we have here? You know, how many different types of rocks do we actually collect? So here we were very excited to get our first sample to measure in the lab. It was just what we call a bulk aggregate material, just loose material that was put into a canister and shipped to us. That's what it looks like. It's actually been stretched here to highlight it. In person, it looks even darker than that. And here, just kind of really stretching to show you that there's angular components in here, a lot of fine material. Some stuff has more hummocky textures. Other stuff is more angular and faceted. But we were very excited to do that. And here's what some of the samples look like when they're mounted for us to do our reflectance measurements, to measure all the different wavelengths we can, kind of look at the same system. And here's what we found. So this is actually the PI of the mission, Dante Loretta. This was in his kind of big paper that came out about initial results. These data over here, these plots, the kind of gray and the purple and the dark blue, those are all spacecraft data of Bennu, showing that blue or flat slope. And here, this other blue one cutting across, that is the laboratory data of the sample. It is red slope. It has a sharp hydroxyl OH band and not much H2O. It doesn't look anything like any of the spacecraft data, not at all. And this is just a kind of bulk aggregate material, right? In fact, if you compare our data of Ryugu and of Bennu, they look astonishing. So similar, in fact, that when my colleague who did the first measurement, he emailed me the data, and I was like, no, I don't want the Ryugu data, I want the Bennu data. And he's like, that is it. It's like, what? And there are other ones we measured where that you just could not tell them apart. So this really threw us. And we said, what is happening? It demonstrates that we also now know that the material from Bennu, the kind of isotopes and other things like it is just like Ryugu. There is very strong evidence that these objects actually did come from the same shattered planetesimal, right? So the rubble piles, they probably came from the same original planetesimal. Their raw bulk fine powder looks very similar. What's happening? Why do the spacecraft data of Bennu look so different? Why is one of them blue sloped and one red sloped? So I know I've gone on a long time, but I want to tell you the conclusion of the story, and we'll skip through it quickly. We usually consider three factors for what drives these differences in slopes. One is the particle size of the material. Large things can tend to impose blue slopes. The other is space weathering. We know on the moon that tends to make things red sloped. But for some of these dark carbonaceous objects, people have argued and shown in labs, they might actually become blue sloped with increased space weathering. And I would say that is the primary thing people have been pointing to suggest why Bennu is blue. It seems to have an older surface than a Ryugu and might be more space weathered and thus have become blue over time. The other thing, though, is, well, what about composition? Maybe there are different things of these objects that could be driving. And what I'll try to argue, let's get through here, is that that the latter one, composition, though most people we don't typically think of this for asteroids and having such an important contribution to this, it might actually be the driving factor for this event. And it's not just anything. It's very specific components on Bennu that we've seen that might be driving it. So again, there's different boulder types on Bennu. These dark hummocky ones, slightly brighter kind of angular ones. We see this manifest in the tiny sample particles we brought back as well. There are angular ones there and hummocky ones. And they have different types of factors to them. This is one of these hummocky ones showing you. It's actually a breccia composed of little rocks, fragments that have been welded back together. Whereas the angular ones seem to be much more homogeneous and solid. They have different physical properties, and the way they fracture and break is clearly different as well. But there's diversity, a lot of heterogeneity on these objects. And we can separate them out and we can measure the quote angular blocky stuff in the hummocky. Say, well, what do they look like? Maybe one is blue and one is red. Nope. They both are red sloped. They look more or less identical, right? And these are the things that dominate the surface of Bennu in terms of the morphology and shape. So and we know that particle size alone can't do it, and the shape doesn't seem to explain it because Ryugu also has big particles and blocks, and so none of that's explaining. So now we're down to it's either space weathering or a compositional effect. Well, space weathering, actually, I'll skip over that. It doesn't matter. Space weathering products have been observed on these objects as kind of like little melt splash things and micrometeorite holes and fragments. So we know it's occurring and it's altered the surface. The question is, how much is it actually altering? We have not been able to isolate these tiny, tiny little things yet to get individual reflectance measurements on them to see. But what we do know is that these products are there, but they're not coating every single particle and object. So space weathering is happening. It's not higher that can really impart these sorts of blue slopes. But what about composition? We also know that Bennu, this is a plot of carbon and nitrogen. Bennu is up here. It's extremely enriched in carbon and nitrogen compared to a lot of other materials that we've measured, carbonaceous chondrite meteorites and Ryugu as well. The nitrogen is particularly interesting. The other thing I'll note that brings us to the story of why we're so fascinated by this material. So far within the Bennu sample, they have detected 14, it might actually be 15 now, of the 20 amino acids that are used in life as we know it. It also has the 5 nucleobases, 4 for DNA and 1 for RNA, right, are all in this material. The other thing that it has, that's the kind of the punchline of the story here is, any guesses? And I guess there could be multiple correct answers for this today, by the way. What maybe one of the most important elements for life is? Other than, don't say carbon. We'll assume that. What other elements? Anybody take guess? Like probably the most fundamentally important thing for life. Guesses. Makes up the backbone of DNA. So phosphorus. Phosphorus is exceptionally important for DNA structure. This material, what we observed, it has these phosphorus-rich components. And this is truly bright material. So when we observe this speckle, everyone's like, whoa, what is that? It turns out this super bright material is enriched in phosphate, and it also has a lot of organic compounds associated. Now, it seems to be filling in fractures in some of these rocks, meaning that there were fluids circulating through it and it was precipitating this out. It was probably the very last thing to precipitate out. There's also some other salts in it. But somehow you are concentrating phosphorus in the fluid circulating through this, along with organic compounds. And the reason we care about that is because that's exactly the type of process you would need to keep going step by step by step to get more complex organic compounds, which ultimately you're going to have to get to give rise to life. So just to be clear, there's no evidence there was life on this asteroid or planetesimal or anything like that. We're talking about the realm of prebiotic chemistry. And what we want to know is how far down that path were we going to life in the prebiotic world on these objects before it all got dumped on Earth. Because again, this stuff is raining down on Earth as it's forming. And that's all of the water on our planet came from these materials and compounds. That's where we get it, along with these organic compounds. So what was happening on the object that then seeded Earth? And it forms these interesting coatings that have these kind of fascinating shapes and textures. It's extremely fragile. And it is not particularly stable, but it is in these materials. And if we go back to our 2 samples that were these angular and hummocky, this third type, what we call these mottled stones that have this phosphate, well, what does it look like? It looks like this. It's strongly blue sloped, really strong, has a giant water band because this stuff is chock full of H2O, molecular water, right? In fact, to date, we know it is the only material in this sample that has H2O in it in an appreciable amount and that has a blue spectral slope. The catch is there's just not that much of it in. Pieces of this phosphate material were also actually observed in the Ryugu sample. Tiny little flecks of it were in it. So it does seem to be present on Ryugu as well, but maybe not in as high abundance as it is on Bennu. And this is just showing you kind of an example of what all this stuff looks like. So the panel on the right here is showing you these bright modeled steps. So our argument has been, even though it's volumetrically not the most important thing on the asteroid, in terms of what's controlling the spectral properties, it might be dominant. So you might have a few percent of this. And over time, as it breaks down and gets fragmented, it gets mixed up in the dust that's coating the asteroid belt. And it might be dominating, or at least having a strong contribution to the reflectance signature, even though volumetrically it's not that big of a deal. Right. So that's kind of a working hypothesis that we have. And you can see, you know, within a given stone, a dark region here, something like this, our classic kind of Bennu sample, right, or flat slope OH, whereas the phosphate-rich stuff has a blue slope and a big water absorption. So we can imagine if we kind of mix these spectra together in different proportions, we might be able to reproduce what we see with the spacecraft data. And this is just to show you, we can use microscope reflectance measurements and so forth, do all sorts of tiny little spot sizes on individual particles, and there's a lot of variability in it. But again, the main thing that I want to walk away with is that it really is this phosphate material is the only stuff we see that has a blueness to it in terms of its spectral properties, and that has water, H2O. So I'm going to skip forward and talk about one more implication here. And so what does this all mean about the parent asteroid? So the family that these are associated with, the asteroid family, is called Polana. And Polana is the largest object. It's named after the largest object in the family, Polana. So what does Polana look like? Is it blue slope? Is it red slope? If these two rubble piles are associated with it, what the heck does it look like? From the telescopic data, it's really hard to tell. It's kind of a bit of a mess. Some things look mostly reddish. It seems to be not really blue like Bennu. If anything, it's more reddish like Ryugu. But again, data aren't great. But we can look now at the longer wavelength region because we have some pretty nice data from a little thing called JWST. And here's what Polana looks like. A sharp OH band, red slope here, and look at that. Out here in this region, it looks just like our bulk samples of Ryugu and Bennu. But in the visible range, it is blue. So it has this interesting property that it's blue here, but a red slope here. And again, this is telling us something about how these asteroids might be evolving over time. And here's just showing you from our paper by Ardano et al. Again, a comparison. They actually use our data, our Ryugu samples and others measured and compared them to show that Polana here is a very, very good match to the return samples from Bennu. So these are all connected. Another one I'll show that's of interest are some of these other large dark asteroids. So is there an object out there that maybe represents something like the original planetesimal before it got shattered? Because we're just looking at Polana and Bennu, there's the remnants of this larger planetesimal. But is there something out there that maybe is intact that was like those? We don't know. But what we propose is there is the asteroid 2 Pallas. And it's intriguing that now with JWST data, we see that it has this sharp OH band, looks very much like what we saw in Bennu and Ryugu. But it has a broader H2O band here as well. And it has a blue slope. And so it's intriguing. And this is just showing you one example. The black one is Pallas. And the red one is just from one little fragment that we measured from the Bennu. So not to say that they're exactly full, but there are things in Bennu that look spectrally like Pallas. And so what we would argue, at least I won't hold my co-authors to it, but I'd say it might be that Pallas is an intact object that made it through. And if we want to understand these prebiotic processes on an intact object, maybe a mission to Pallas to understand it or to sample it or land on it, observe it, would be the next kind of logical step. Understand what the inventory is out there for all the raw ingredients that we need for life as we know it, because so far they seem to be on these types of objects. We're learning more about this. So that's my story.
So when you look at Pallas, say with JWST, what does it look like? Does it look like a spherical object, or does it look like broken up?
It's not a rubble pile. It's too large for that. It is an intact object for the scale and size of it. It is not a dwarf planet like Ceres because it's not large enough to have achieved hydrostatic equilibrium to kind of achieve a round enough shape under its own kind of mass and gravity. So it's not that realm, which is what makes Ceres a dwarf planet because it's met that criteria. Ceres is the only thing in the main belt that really meets that criteria. So it's a large intact object, but so not a rubble pile. But what does the surface look like? We don't know. It probably, if I had to guess, probably something more like Vesta, where it's kind of regular, it's dominated, smooth, cover lots of craters and things. So not a rubble pile, boulder rich sort of thing, like Bennu's Ryugu, but would certainly have boulders on the surface from impact events. So I suspect probably something like the asteroid Vesta, more finer, a lot more finer regolith than these rubble pile asteroids. Other questions?
In the image where you show, after the sample is taken, the return, and you see the crater and it looks red.
Yes.
Is that because that's a lower layer that hasn't been exposed to the radiation?
I laugh because that is an ongoing debate as to what we know is that first of all, in the diagrams they use, they often show it as redder. And actually what it is I would say it's less blue to spectrally flat. Nothing on the asteroid actually became truly spectrally like red, like what we see on Ryugu, but it definitely became less blue and darker as well. And so it could be one of several things or combination. One is it's because you've smashed a lot of stuff together and the finer particles, it is darker. The finer particulate material is darker. And we know that's true of these objects. The finer material is darker than coarser material. So that could be explained and also cause a change in the spectral slope. The other factor could be that you've excavated fresher material from depth that has less space weathering. And so for the folks who want to say the blueness is due to space weathering, they point to that and say, look, we sampled from that crater because it was a younger looking crater and it was redder or less blue to begin with and darker. And we excavated it and it's more so because it's fresh and it's not big space weathering, which is reasonable. I suspect what's happening, it's a combination of all of these things. And that's what makes it so difficult is you can have 2 or 3 processes that are giving similar results. And so then it makes it difficult to disentangle for any given observation or case. What's the primary reason? Is it particle size? Is it because it is less space weathered? What's happening?
Question.
Yeah. You mentioned a few times the finer particle regolith tends to be darker. Is that just a result of the geometry of the optics as the particles approach like wavelength size? And do the samples get separated out into different grades of particle size to try and get a better measurement on this?
Yeah, good question. So it's actually unusual because for most geologic materials, they become brighter as you get finer grain because you're getting more light bouncing off the first surface reflection order as opposed to going in and interacting and scattering out. And so most things, as you powder it up finer and finer, they get bright. It's very unusual for something to get darker, but that is what's happening with these materials. And we don't understand exactly why that is, but it must have something to do with the actual very complex, fine, intricate internal structure of this material in terms of how it's trapping photons when they get in there and actually creating more surface area makes it more efficient at trapping that or absorbing it. It's a debate as to what exactly is driving that. In terms of are there separations as you sieve it, I think naturally when this is happening, it's finer particles from. It's hard to say. Some of the boulder types, we now have physical evidence that certain boulder types in Bennu, the hummocky versus angular, they do fracture and behave differently and have different mechanical strengths. So some of those might be contributing more to the fine particles than others. But in the sample we've returned, we see all of these in the fine particles at all different sizes so far. But does that answer that?
I think my question was, has anybody proposed taking the sample and like mechanically separating out the different size particles.
So we actually are going to do that next week with ours. Now there are instruments back up anyway, because that was one of the things we want to do is actually take those two stones I measured that I showed you that we measured. We are actually going to do a light crush of it and separate it. And we'll just do a couple whacks or two to kind of crush it and have it fracture on its own like that. And then take the larger ones and separate them from the finer and measure them to see what happens to larger and finer. And then we might go beyond that. That's one of the things we were kind of specifically supposed to do with our sample that we allotted before we send it back to Johnson's.
So you gotta come back and tell us.
I'll email you. I can tell you. It's like we suspect it's all still going to be red and get red. The question is, will it get redder or anything like that? Darker. We suspect from previous things that people like as we go to finer, it will probably get darker. We think, and maybe redder, but we'll find out.
Thank you.
Thank you very much.
Yeah, we are done. There's refreshments in the back. Thank you, Bob.
I have a question online.
We do have a question from Greg Shanos.
Okay. Greg, I'm printing you out.
Okay, where is the water in Ryugu in the phyllosilicates, or where is it? Is it trapped?
Yes.
I don't know if it's not H2O.
That's exactly
Okay,
the
now
water
the
is in
new-
the phyllosilicate minerals, and that's why it's all OH. We suspect what's happened is, and it makes sense when you think about that, when you're in the vacuum of space at the surface of the asteroid, any H2O that might be trapped in swelling clays or phyllosilicates, that wouldn't be stable there and be pulled out in the vacuum anyway. But the OH is part of that structure of the phyllosilicate minerals, and it's always going to be in there unless you totally thermally dehydrated or destroyed that way. So that's why we see only the sharp, narrow OH band in the pristine state, because it is just the phyllosilicates and it's primarily serpentine phyllosilicates that only have OH and no H2O anyway. There's other ones in there that under Earth, they will absorb H2O. And that's what we see happening with exposure to Earth atmosphere. That material does suck up H2O in some of those phyllosilicate minerals. But in the pristine state out in space, shouldn't have that.
Thank you.
You're welcome.
One more question in the back.
One more question.
Yes.
I've been interested how small observatories can be really very productive doing asteroid rotation studies.
Yeah.
And trying to explain that to friends. I typically say, it's just amazing how much you can learn about an asteroid from knowing its rotation period. But the fact is, I really don't know what I'm talking about when I say that, to rationalize. And I noticed a little outside what you were speaking about tonight, but I have a hunch you might be able to comment on what can be learned in general from asteroid rotation studies. Can you comment on that so I can maybe quote you?
I don't know if I go that far.
Yeah.
Okay. Off the record. So I would say that first of all, there are some citizen science groups out there who are doing some really good things with helping people, amateur astronomy groups and others to kind of use telescopes to do things to get like light curves and rotational observations. I think, there are definitely things one can learn from getting those light curves to understand, well, first of all, how homogeneous is the object and its reflectivity. If you start to see variations, that indicates, well, something's different. Is it, smoother, finer particles on one part of the asteroid and coarse grain on the other, or craters or something like that? So even that alone, just to see, well, how much does it vary? That can be, very useful. And further to kind of, if you kind of couple that with, the overall albedo level of the asteroid, or even if you have other data of it to know what spectral type it is, then, you can add to that within the classification schemes to say something about it, or just to understand those rotation periods alone can be very, very helpful as well, just to know how fast they're spinning, because that has implications about the orbital dynamics and their histories and so forth. In fact, and again, don't quote me on this because I'm not the dynamicist, and so I'll probably get this wrong, but one of the surprises when we got to Ryugu was that it did have this diamond kind of top shape that was not expected for that size. It wasn't expected, or for that size and its rotation rate. So it kind of implied, or at least I think some people interpret that it must have been spinning faster in the past because of that shape. But again, there were estimates of the kind of shape and stuff, and because of light curves and so forth like that, and knowing the rotation rate. So it is useful.
Yeah, right.
It's shaped that way because it's the color of a charcoal briquette.
Exactly. I know that's what it seems like. Yeah. Although I will say, observing an asteroid like this with a telescope is challenging to say the least because they're rather dark.
Thanks everyone for coming. Appreciate it. Thanks, Dr.
Thank